Welcome, my name is Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting projects to help you hone your programming skills. Today's project is a classic. It's the flocking algorithm. It's originally developed by Craig Reynolds back in 1986, so like I say, quite the classic. I want to put a different spin on it though. In addition to our standard flocking, I want to present it as a way to control enemy units in, for example, a game. So instead of thinking about this just as a flocking behavior for, say, birds, we can use it for things like light cavalry or cavalry archers, or if you prefer science fiction, fleets of enemy spaceships. And it gives a really nice movement pattern for controlling enemies in, say, a game environment. So the basic idea for flocking is it's a way to simulate how agents can move together. And in fact, originally it was written for birds as a test. Is this one of the ways that flocks of birds could be navigating? So there was a big scientific question of, do they have a leader that they're all following, or is it somehow a self-organized system? And this was proof that it at least could be a self-organized system, that simple rules that each bird follow is enough to get these complicated flocking behaviors that we observe. Not necessarily proof that that's what birds do, but very strong evidence that that could be what they're doing. And since then, people have been pretty convinced, yes, it's these sorts of rules that birds use to maintain their flock structure. So how do the rules work? The idea is we have a set of agents. Think of them as birds if you want, or spaceships or cavalry units. And we need to determine how each one is going to steer. And so I'm going to do this for the blue agent here. And there are three factors that come into play. So the first one is what's known as separation. So we draw a circle, fairly small radius, and any agents within that circle our main agent wants to not run into. So this is to avoid crashing into nearby neighbors. And so the idea is we look at, well, what is the average position of the ones we want to avoid under separation? And then we calculate the vector to that position and then look at actually its opposite because we want to move away. One of the nice things about the flocking algorithm is it uses a couple of variations basically of forces. So it's a good way of seeing how we can apply different forces. In particular, for separation, we want a distance-based force. So the closer two individuals are, the stronger we want to turn away from them. And this ends up being, as we'll see in the code, basically 1 over the distance. So as the distance gets smaller, you get a bigger, if you will, repulsive, or really a bigger steering force. Then the second thing we do is we draw a bigger circle of sort of our general set of neighbors. And for those, which are these ones in green, we look at two things. First, their average position, and we want to turn towards the average position of our neighbors. So that's sometimes referred to as cohesion. An agent says, well, I want to be close to my neighbors. One of the interesting things here is the ones that are too close are also counted into that average. And that may seem a little silly, but computationally it's easier just to say everything inside this circle we're going to add together and steer towards them. To balance that out, what you'll see in the code is we have constants, and typically the constant that gets applied to the cohesive steering force is smaller than the one for the separation. So we put a bigger constant on the separation. So if you get too close, you steer strongly away. If you're not too close, then you try and steer to be with your neighbors. It turns out, although this seems like enough, it tends not to be enough, particularly, and I don't have the example shown here, if, for example, this individual were flying in the opposite direction, it would try and get close, but then it would just pass them. So the third force, which is a very important one, is what's known as alignment. And the idea for alignment is we look at the average heading of all of these neighbors. And so I've put that in as this vector. And then we want to also steer in that direction. So each agent is trying to steer based on three factors. Avoid anybody you're too close to, steer away from them. Head towards your neighbors, so stay close to your neighbors, but also align with your neighbors. And one of the interesting things I want to highlight here, and it'll show up even more clearly in the code, is the first two forces are based on position. I want to avoid the position of my neighbors that are too close, and I want to head towards the average position of my neighbors that are reasonably close. This third one is not based on position, it's the heading. So I want to take the average heading of my neighbors and head in that direction. So for the first two forces, we have to change a position into a steering force, and for the third one we don't, because it's already a heading. And if that's not clear now, it will become more clear in the code. But in general, anytime you're sort of dealing with this steering idea, it's useful to think about, is it a position that I'm interested in going towards, or is it a direction that I'm interested in aligning with? And that has a very small difference in the code, but an important one. And so just keeping those two ideas clear in your head. Am I heading towards a location, or am I aligning with a particular direction, can make writing the rest of the code much easier. Okay, but in general, we need separation, cohesion, and alignment. And before we set that up, we need, of course, a whole flock of birds that we can have moving around. One other thing I'll mention, you'll notice I have them in here as little triangles. I'll put that into the code as well. That is sort of a holdover actually from Reynolds' original work. He was doing it in NetLogo, where you have what are called turtles moving around, and their default shape is a triangle. So we sort of stick with that, and you'll often see, if you look at flocking demos, that the agents are all represented as triangles. That's a callback to NetLogo. If you're interested, I do have a couple of videos that use NetLogo. There's kind of a fun one with evolving zombies that get better and better at chasing down humans. I'll put a link to that if you want to check it out. But historically, that's why we're representing these as triangles. In practice, what you almost certainly want to do, of course, is replace it with a really cool image of, say, cavalry or spaceships or birds or fish, whatever it is that you have going on. Okay, so now let's take a look at the code. As with many of my projects, I'm going to be doing this in processing, which is a programming environment. You can use several different languages with it. I'm going to be using Java. You can see over here, I'm using the Java version. There's also a JavaScript if you'd prefer that, and in fact, a Python as well. Or I'm mostly talking about the algorithms, which of course you can encode in any language you like. Because this is processing, I've got a little bit of boilerplate setup, which creates our window for us, and draw, which is sort of an infinite loop that keeps updating the screen. And I'm going to be doing this from sort of a top-down perspective. So I'm going to start by creating my flock of birds just as an array list. And birds don't exist yet, so that's going to be a class that I'm going to have to define, but I want to sort of set up the rest of the code first, and then we can get into defining that class. So here's where we start. I create my array list, and then I'll just begin by creating 50 birds. So I go through a for loop and add each bird to the flock, and I'm just going to put them at random locations. So X is the random width of the window, and Y is the random height of the window. And again, getting an error because I don't have bird defined yet, and I believe also missing a parenthesis. Okay. So assuming that the bird class exists, then I can go into my draw loop, and I need to update them. The first thing I'm going to do is fill in the background, so that erases the window or fills it in with black each time. And then for each bird in the flock, I need to do a couple of different things. I need to sort of guide it, so that's applying all of these steering forces. Then I want to update its position, and then I want to display it. And as is typical, the changing its heading, which is really changing its velocity, so what direction it's moving in, is done in one step, and then updating its position is done in a separate step. So basically, internally, all of my agents, all of my birds, decide how they want to move, and then they all move simultaneously. And that avoids any artifacts that you might get by having some of them move before others. So in terms of the code, that's pretty straightforward. I'm going to call this my guide function, which is how they adjust their velocity, their steering, and then I'll have them update their positions, and then they can display themselves. There we go. And that's really all we need for the main code. But of course, now I need to go in and create all of these functions as part of the bird class. Each bird has a few different pieces of data that it needs. And one of the things that you need to decide here, that I'll talk about a bit as I move on, is which parameters do you want to be unique to individual birds, and which ones do you want to be for all birds? So in particular, I talked about the constants for how strong is the separation force and how strong is the alignment force. Those could be the same for all birds, or you could put them in differently for each bird. And I'm going to make them the same for all of them. So I'll end up making them global variables. And that will become a little clearer in a minute when I start putting it into the code. What the birds absolutely need to have individually is their position and their velocity and their acceleration. And I'll make all of those vectors because we need them, to be headed in a direction. You've got a velocity in a particular direction. The type I'm using here is a p-vector, which is built into processing. Most languages that you'll work with have some sort of a vector data structure that works basically the same. And then we need a constructor. So there's my constructor. And again, just for a little variety, I tried to do each of the vectors in a different way. So the position is based on that random height and width that we passed into the constructor. So I'll create a new p-vector with that random location. The velocity, I'm using a built-in function random2d that gives you a unit vector, so a vector of length 1 that could be pointing in any direction. And then the acceleration, I'm giving them a new p-vector, but doing it as 0, 0, so they have no velocity to begin with. And then the next function that we need is the guide function. And I'm just going to put in a placeholder for that for now. So I don't want to worry about the guide code yet, but because I did put it into my draw loop, I do need to at least have a placeholder function, which is always a handy way to sort of develop these things. The other thing that's worth mentioning, my flock is a global variable, which is pretty standard for processing. So I don't necessarily have to pass it in as an argument. The reason why it is nice to pass it in as an argument is I might get a situation where I don't want one flock, I want two flocks. And maybe they use these rules to cohere together as the same flock, but they use a different set of rules to, for example, avoid each other. And so I want to think about, in general, the guide function as being something that I pass a flock into, so that I could have here another function, which is the attack function, where I pass in the enemy flock. So that's why I'm using it as an argument, even though it is a global. So that's, like I said, just my placeholder for the guide. Then the next thing I need is my update function. And this just updates the individual position of each bird. So I begin by taking the velocity and adding the acceleration. And at least initially, of course, the acceleration is going to be 0. So that won't have any effect. But I do want it there as part of the code. Once I have the velocity, I can then add it to the position. But before I do that, I want to put in a limit. If you want to simulate things like birds, they definitely have a maximum flight speed. So that's good to put in. So there, I'm limiting my velocity to that maximum speed. And notice that things like add and limit are built-in functions that are part of my P vector class that comes with processing. So if you're not using processing, you might not have these functions available and you'll have to figure out a different way of handling them. If you have a language with vectors, it almost always has an add function, so you can add two vectors. The limit is a little fancier, nice to have. I'm getting an error, of course, because max speed isn't defined. This is one of those variables that I could either make unique to each bird, so each bird has its own unique max speed, and that could be nice if you're, say, doing an evolutionary algorithm and you want the birds to be able to evolve their top speed, or if you're setting up a game where you have different enemy ships that have different maximum speeds. For now, I'll take the slightly easier route and just go in and make it a global for all of my birds. And I'll just set it as 2, which is perfectly arbitrary. So now that we've limited the velocity, I can add that velocity to the position. So let me scroll here a little bit. So add in the velocity, and I want my agents or my birds to wrap. So I've got to put in a little code so that they'll wrap around the edge of the screen as well. Spell position correctly. So this will give me the wrapping effect. And then the last thing that I need to do to be able to run at least my base code is to put in my display function so that they'll draw themselves. And what I'm going to do is translate my coordinate system to where the agent is located or where the bird is located, and then rotate the coordinate system so that I can draw a nice little triangle there. So push matrix takes the current coordinate system as a matrix and stores it on a stack. And then when I'm done drawing this bird, I'll pop it off and go back to the original coordinate system. So as I said, I'm translating to the location of the agent that I want to draw, and then I'm rotating so that my coordinate system is the x direction is the direction that it's facing in. And again, heading returns the angle of a p vector, a nice handy function to have. And I'm drawing these, as I said, sticking with the classics, drawing them as a triangle. So here are the 3 vertices for the triangle. With processing, I do that as a begin shape and an end shape. And then the close here, make sure that it's a closed triangle. So it's going to finish off the triangle. And that's really all I need to display them. And now I've filled in at least preliminary versions with guide as just a placeholder for all of my main functions. And so if there's no typos, I should be able to run this. And there is. The error I'm getting is I can't use push matrix that many times. And the problem, which you probably noticed, I said I would need to pop it off, but I forgot to do so. So that returns to our original coordinate system so that we can then change it again to draw the next bird or the next agent. There we go. So there's all of my triangles moving around. They're not doing anything interesting in terms of steering. They're just moving in a straight line based on their initial velocity. And these are a little smaller than I meant them to be, so I think I'm going to make them a little larger. So let's change these sizes. Just put in some 1s in front of that. There we go. That's a little better. So there's our agents moving around, not doing any sort of steering. So we need to start putting that in. So now we need to start filling in the guide function. So let's take a look at that. And I'm going to set this up to, in a sense, minimize the code a bit. So really the guide just needs to do 2 things. It needs to set the acceleration to 0. And the point of that is just that acceleration doesn't carry over from one time step to the next. And then I'm going to call a steering function and hand it the entire flock. What often happens here, if you look at different versions of the code, there'll be a separate function for each of the three sort of forces. Each of those has to loop through the entire flock. And in terms of making the code a little shorter, it's actually easier just to set it up as one function. Programming design standpoint, it might be better to break it into three. I'm going to do it as one for compactness. So we need our steering function. And here we need to calculate those three steering vectors, the separate, the align, and the coherence. And those are generally based on a sum of their neighbors. So I'm going to create some p vectors to store those sums. So there's the three new p vectors that I need. We also will need to know how many agents are in each of those neighborhoods. This is going to keep track of the neighbors that I'm trying to align with, and this is going to keep track of the neighbors that I'm trying to avoid. And with those two in place, I can now go through the entire flock. For each other bird in the flock, need to calculate the distance to that other bird. So the distance from this agent's position, the one running this function, to the other agent's position. And then I need to do a couple of checks. So if the distance is larger than 0, and the larger than 0 does two things. So one, it makes sure I'm not calculating the steering forces between an agent and itself. That causes problems, especially because I'm going to end up dividing by d, and I don't want to divide by 0. And then the other check is to make sure that I'm within the neighborhood region. Within that neighborhood region, I'm using the alignment and the coherence forces. So I need to do those calculations. So for all of those other agents that are within my neighborhood, I'm going to add their velocity to the alignments. So I'm figuring out the velocity is the direction they're heading in. I'm adding all of those velocity vectors together. And then for the coherence, I want to angle myself towards their average position. So there I'm adding all of the positions together. And that's what I was talking about earlier, sort of keeping in mind, which can get tricky, when am I interested in their heading, their velocity vector, and when am I interested in their position? And then I just need to make sure I'm keeping a count of all of these. So I will add to my count. And that takes care of the neighbor forces, the coherence and the alignment. And I got a couple of errors here. First, a typo in flock. Let's fix that. And then the second one, that's actually dist, not distance. And the third one is I haven't defined my neighborhood distance. And again, this is a place where I could have each agent have its own neighborhood. Interesting if you want to create a bunch of different kinds of unit. In this case, I'm going to take the simple route and just make that a global variable for all of my agents. And I'll start it as 50. I might need to make that a little bigger because I've got pretty big agents in this case, but that's not a bad place to start. This does the calculations for alignment and coherence. I also need to do the calculation for separation, which looks fairly similar. The big difference in the check is that now I have to worry about the separation distance, which again doesn't exist, so I'll need to go and define that. And the separation distance has to be smaller than the neighbor distance because the separate distance are the agents that I'm turning away from. If those two are equal, then I'm balancing my turn away and my turn towards, and I'll have no effect. So for those agents, what I need to do is calculate the distances, so sort of like the other positions. But as I said before, I want this to be dependent on that distance. So the closer you are, the stronger the repulsive force. I need that difference. There we go. So I'm taking the difference in their two positions. That gives me the vector between them. And that's similar to what I did up here, except this was just giving me the distance, so I knew how far apart they are. Here I'm actually doing a vector subtraction, so I'm getting a vector between them. And then what I'm going to do is take that vector, normalize it so it's of length 1, and then divide by the distance. So this gives me a vector that actually gets longer the closer together they are. And then I'll add it to my sum. And increase my count. Okay, so the idea for both of these if conditions are pretty similar. Add up the information about the ones that are within the neighboring distance and add up information about the agents that are within the separation distance. And where it gets a little tricky is sometimes we need velocities, sometimes we need positions, and sometimes we need vectors that are based on the inverse of the position. Okay, so now that we have that, I can start applying those new vectors to the steering. And I'm going to do that in two pieces. So let's come down here and I'll begin with the separation. So the first thing I'm going to do is check to see if the count is larger than 0. If it's 0, it means there were no agents nearby and I don't need to do any separating at all. If it's larger than 0, that means that there are some agents that I have to avoid. And I'm going to avoid them by creating a new function called target. And I'm going to pass into target that vector that I want to align to. So the idea is this sum separate vector is here's where my agent is. Here's, for example, the agents that I want to avoid. I've now calculated a vector that points away from them, and I want my agent to align with that. So I want it to sort of target that vector. But as I mentioned before, depending on which vector I'm dealing with, is it the separate or the coherence or the alignment, I might want to put in a different constant. So I'm going to define a separate constant that affects the force of that retargeting. This, of course, hasn't been defined. And as I've now said twice, I could make it unique to each bird, but I'm not going to. I'm just going to make it a global for all of them. And this is a fairly arbitrary number. What I'm going to end up doing is for the coherence and the alignment forces, I'm going to make their constants 1. So as I said before, the separate should be a little larger, so it forces things to separate more strongly than they want to cohere so that we don't get any collisions. And now what I need to do is define that target function. So I have the target direction that I want my agent to start to align itself with, and I have the K, how strongly do you align? And then there's a bunch of code that we do here that I'll put in and then explain. So the first thing is I want to normalize the length of that vector. And then I multiply it by the maximum speed. So I'm taking the vector, making it of unit length 1, then extending it out to the maximum possible speed and subtracting from it the current velocity. So really what I'm figuring out here is the new velocity, which is the direction that I'm headed in, right? I move in the direction of the velocity. If the direction I want to head in is equal to the current velocity, then I don't want to change it. I don't want to change the acceleration. So that's why I'm subtracting the current velocity from this vector. And then I want to limit it so that that can't be too large. And I'm going to limit it to some maximum. And thinking of this as a maximum force that I can apply, because in the end, the target direction is going to be treated as a force and added on to the acceleration. So I'm getting an error because I haven't defined max force yet. That's another thing that can be unique to each agent or a global. I'll make it a global, so let's go put that in. And again, this is a number that I came up with from playing with it for a while, but generally we want very small forces to get a nice smooth motion. So in each time step, we're actually only turning a little bit to align with our target direction. So now I have my maximum force. Then I'm going to multiply it by that constant k, and now I can add this into my acceleration. So that calculates the acceleration, and the acceleration is applied here in the update step. And I realize I got a little carried away with my force. This should be 0.0310, and now we can run this and take a look. And so you'll notice they're no longer going in a straight line. If two of the agents get close together, they immediately turn away from each other, typically in opposite directions. So we're not getting any sort of flocking yet because we don't have the coherence in the alignment, but we do have them moving away from each other. They're overlapping maybe a little more than I like because I made them fairly large. So I'll go in and increase the separation distance. Let's make that 50 and the neighbor distance 100 and see how that looks. So there we go. Now they're starting to turn away when they're not quite as close to each other. And so you can watch as they get close. They turn away pretty quickly. Two reasons for that. We've got a reasonably large separation constant, but also there are no other forces in play. So before I spend a lot of time trying to update my separation, I want to go in and add my other two forces, the alignment and the coherence. So let's go ahead and do that. I'm going to come down here to where I did my separate and put in the same sort of code. First, I have to make sure there are any neighbors at all to do the calculation with. And the first calculation is easy. All I have to do is take the sum of the alignments, which is already a vector, and do the same sort of targeting. I want to align myself with that vector. I haven't defined my alignment constant yet, so let me go and do that. Yet again, it could be part of the bird class so that each agent has its own alignment force, but I'll make it a global. There we go. And maybe just to make things a little cleaner, I will put it up with my other constant k. And as long as I'm here, I know I'm going to need it in a minute. I'll put in my coherence constant as well. And those are both 1, as I said, a little smaller than the separation constant. So now I can do the alignment portion of the code. And if I run this, now we're starting to see pretty good flocking behavior because if they get too close, they move away from each other, but they also try and line up in the same direction. The issue, there's really two issues that are going on. One, the behavior is sort of boring because they align and then just move in a straight line. The other issue, which is not obvious, is if they start to separate, there's nothing pulling them back together because we don't have that coherence force. Because I have a lot of agents, they all do a pretty good job of lining up. But if they were more spread out, if I had a bigger world, they might never approach each other because they're missing that coherence force. So not bad, but it doesn't look very realistic. We don't get sort of the variation in movement that you see, for example, in real birds, and that's because we're missing the coherence. So let's put that one in. So for the coherence, I've added together a bunch of positions. I need to take the average position and then find the vector to that position. So to find the average, I simply divide by the number of agents that contributed to the sum. That's my n count. And then to find the vector, I take that sum of coherence position, so that's the average position of all of my neighbors. I subtract from that my current position, and that gives me the vector between them. And now that I have the vector, I can just call my target function. So now I'm trying to align to that vector, which will turn me towards all of my neighbors to get the agents to clump together. And what ends up happening here, as we'll see, is we've got sort of two opposite forces. One is saying, turn towards my neighbors to clump together. And then the separate is saying, well, if I get too close, turn away. And that actually gives a nice sort of dynamic motion, as we can see. So there we go, they're lining up, they're sort of cohering into flocks, but within a flock, you get a lot of this little bits of sort of back and forth. I want to move closer to the rest of my neighbors. I don't want to get too close. And so you can see little bits of more organic, natural looking motion. It also means that if they start to drift apart, the coherence will pull them back together. So they'll stay together as a flock if anything starts to separate them in some way. Okay, so this is the basic flocking algorithm. You can see what happens if agents sort of come together at right angles. They quickly orient to come together into one big flock. And in general, on sort of a map of this size with this many agents, what you will typically see is all of them flocking together. Occasionally, they'll break apart. One other thing that's worth noting, when it finds neighbors, that does not wrap. So they wrap when they're moving, but an agent over here right on the edge does not look to the agents at the other side of the map. Doing that is a bit more complicated of a calculation that I don't want to worry about. I'll point out where to do it. The issue is here when I calculate the distance. That's only calculating the distance sort of within my window. It doesn't properly wrap around. If you want to wrap around for calculating this distance, you have to calculate the X and the Y separately. And if they're larger than half the map, then you adjust to look at the wrap distance. Gets quite a bit more complicated and is not particularly important in this case because the agents tend to move roughly in a straight line, so they'll wrap around and stay with their flock anyway. This gives nice organic looking motion for things like birds or fish, but as I said, one of the nice applications is using it for, say, enemies in a video game. And so for that, we need the agents to orient on what is for them the enemy. And it turns out that's pretty easy to do once we have the rest of the code in place, as we do here. I'll put in a new enemy function. And like steering, this has each agent adjusting its heading, but in this case to target some enemy. And to make things easy, I'm just going to make the enemy the mouse. So they're going to orient on the mouse position. So I'll make a P vector out of the mouse's position. And then what I need is the vector that goes from this agent, the one that's currently reorienting itself, to the mouse location. So that gives me that difference between those two locations, the vector between them, which I want to orient onto. And that's easy enough to do because I already have my targeting function. And for now, I'll just say the constant for orienting on the mouse is 1. If you look back at the code, this sort of structure is exactly what we did with the coherence force. We found the average location of all of the neighbors, subtracted that from the location of this agent, and then oriented onto the vector between them. So if I run this, what you can see is all of my agents are orienting on the mouse, but they're also flocking together. So if I move a little bit away, they're still using their separation and their coherence to stay as a flock. So I'm basically, in a sense, being attacked by a flock of agents, if you will. This looks a little better if I make my agents a bit smaller. So let me go in and do that. So I'm going to come down here to my display, and let's make these, for example, 8 and 8. And I don't know, 6 and 6. So there's a slightly more medium-sized set of agents, and you can see them flocking together, but also attempting to chase down the mouse. So this works well if you think of them as, say, light cavalry with lances, orient, and then charge at the player. Or maybe they're spaceships, and as they orient, they're shooting at the player. But we can make this a little more sophisticated by changing their behavior depending on how close they are to their enemy. And of course, if I move around, you can watch them trying to reorient on me, which is kind of nice. But let's go up and make the behavior a little more sophisticated by tying it to the distance. So I'm going to now calculate the distance between the two individuals, spell position correctly, so from the mouse to this agent, and then how the agent behaves depends on that distance. So let's say if the distance is larger than 100, I want to turn towards the target. And if the distance is less than 100, I'm going to make my constant a negative, which will cause it to turn away. So let's take a look at how that looks. So you can see them turning to orient on the mouse, but when they get close, they turn away. So this again works well if you're thinking about, I don't know, maybe horse archers. And so what they want to do is orient on the enemy, but then, and this is usually what happens, they settle down into sort of a circulating behavior. So you can imagine this as being a bunch of horse archers charging around in a circle, shooting at their enemy, or I don't know, maybe they're spaceships. But you get a nice combination of behaviors. And if we try to run away, they all orient. And notice that they're keeping the rest of their flocking behavior. So they flock nicely still. They stay reasonably separated from each other, but they charge and then separate. So if I run away, they're going to chase me down. If I move towards them, they start to spread out. And how much they spread out, of course, is adjustable with this parameter. Let's try making it 1.8. Probably a little large, but we can see it pretty clearly. So now their avoidance behavior when they get close is even stronger. So here they come charging in, they get close, and then quick swing around, reform into new flocks, charge and avoid again. So this gives you a much more sort of sophisticated enemy behavior if you want to put it into a game. But it could also work very well in something like an artificial life simulation, where maybe these are fish that are learning over time by adjusting these parameters to gang up on enemy fish, for example, or birds that are learning to avoid a predator using the avoidance behavior. And the general idea is that now that we know how to create a target vector that I want to align to or avoid, we can put in lots of them to get complicated behaviors that balance heading towards some reward and avoiding some threat. This is based on having a single individual. There's nothing that says you can't have sort of a whole separate flock. So we have two opposing flocks that maybe want to cohere together, but also either attack each other or avoid each other. So all sorts of crazy things you can do. You can get really cool visual effects if, for example, instead of replacing the background each time, you allow each agent to leave a trail behind it, a sort of an infinite number of things that you can play with. If you come up with anything really cool, please feel free to leave a comment down below. I'm always excited to see what other people are doing with these sort of starter programs. So thank you very much for your time and happy coding.